Okay, so I should start now, I think. So let me start by some recap from the last time. In the last week, we were talking about an approximation algorithm, log-n approximation algorithm for approximating conductance, and actually its generalization, which is H expansion. And again, just to recall, the H expansion of a graph G is just a quantity which you minimize the ratio between the cut size in G and cut size in H, minimizing overall cut, right? And how did we approximate this quantity? We look at the relaxation. So we write H expansion of G as an optimization problem where we minimizing overall cut metric, right? Just rewrite it as that. And then instead of minimizing overall cut metrics, we just relax from cut metrics to all metrics and denote that by latent round relaxation here. So just change this thing to this thing. And we just minimizing this thing. And this relaxation, you can model it as an LP. And we saw this LP. And because of that, you can compute it. And once we know how to compute this latent round of GH, then we show that actually it is actually a good approximation within log-n factor. So the relaxation obviously is at most the quantity, but it's not worse, like it's not too small. You have log-n factor only here. Okay. And there were two ingredients to show this. One is that any metric can be embedded into L1 with just log-n distortion. Like any metric you can embed into L1 with log-n distortion. And any L1 actually is just a combination of cut metrics. So that is the two things that we use. All right. So that is just for last week. So this this class, in this today, we wanna show, we will talk about some generalization of the min-cut max flow theorem that that you might have seen from some other class. And why do I do this? This is because actually it will be essential to show another characterization of expander based on flow. As I mentioned in the first lecture, like there will be like 4 or 5 characterization of the same notion expander. Flow will be one of them. And to talk about that, we need today's class. But this generalization of max flow min-cut theorem by itself is interesting. So you will, I hope that you find it interesting. But okay, before we even talk about to even state the theorem or talk about the problem that we look at, I need to tell you, like to define some definition. So let me start by recall some basic definition about flow that you might have like maybe learned from previous class, which is just ST flow. That is, suppose that you start by like you look at the graph G with H capacity, kappa for capacity. So and you have non-negative capacity, right? And then let me denote this script P of UV to be all the set of, like the set of all UV paths, all paths from U to V, right? So P, like this is U, this is V. Any path here is in this set UV. All right. Now, what is ST flow? And ST flow is basically just a function that assign non-negative value to this, to the path, to the ST path, right? So if you have this S and T, and then maybe you have the first path, P1, maybe there is a second path that might use the same H, or the third one. You literally just assign the flow value along the path. The first one maybe 10, second one maybe 3, and something like that, right? And so the flow value from S to T here is really just a summation, like, by the way, the value on the path, I write it like this. So the flow value on path 3 is now 2. Okay. And the value of the flow is literally just the sum over, like the sum of total flow that you send. So in this example, it's gonna be 15, right? 10 plus this plus this. So next, I wanted to define a congestion, the congestion of the flow. So if we want to, like, the congestion of the flow on HE is the total amount of flow on E relative to its capacity. That is, the congestion, this is defined to be like congestion of flow on E is a total, like total flow value over all paths that contain E, and you divide it by the capacity of an H. Okay, so and now the congestion of the flow itself, I just maximizing over all edges. All right. For example, let's say that this graph have unit capacity on every edge. All right, and and let's say that this is an edge, right? Then the congestion on this edge is going to be 2 because it is used 2 times. If the capacity of this edge is 10, the congestion on this edge is going to be 0.2, 0.2, right? Make sense? Sorry?
We are summing the f of p.
Oh, right. Sorry. Yeah. So the congestion is so sorry. The congestion should be like 10 plus 3 over the capacity. So if the capacity is 1, it's going to be 13. Otherwise, if capacity is 10, then you just divide it by the capacity. Yeah. All right. Sorry about that. Yeah.
Is there no restriction that f should be assigned that capacity should not be crossed?
What do you mean?
So in this case, congestion is more than 1, right?
Yeah.
It's not there is no restriction that congestion more than 1.
No, there is no restriction. If in other class, maybe you want to say that you want to find flow such that congestion is at most 1. Now we just said there is some flow. You just measure the congestion. Yeah.
So what does it mean, like the flow through the edge is more than the capacity of the edge?
It just means that you exceed the capacity by that much factor. Okay. It just means that if you scale down everything by the congestion of the flow, then you get a feasible flow. Okay. Then everything is respect the capacity. Yeah. Okay. So this is a thing that you have seen in previous class, and it is about you have the demand. You want to send a flow from one point to another point from S to T, right? And max flow problem is how much you can send flow as long as the congestion is at most 1. But what if can we try to talk about what if there are more than single demand pair? And yes, of course, right? How are we gonna model this? We will try to model this using a graph. So I will just define it to be you define the demand graph H, all right? And the graph H, let's say that they have the same vertex set as G, but totally different H set and different capacity. And we really think of each edge in demand graph as the demand pair. So an edge ST in the graph H basically represents the demand from S to T. That is, we want to route flow from S to T. By how much? That will be the total of flow that we would like to route from S to T will be measured, specified by the capacity of the weight of this edge in edge. Right. So, for example, let's say you have a graph G, and you have a graph H, and let's say H has 2 edges, S1, T1, S2, T2. Then, basically, this thing kind of tell you that you would like to kind of find a flow that, and let's say this is 1 and this is 10, yeah. Then the goal is to kind of find a flow that one set of flow that send, let's say this is 3. Maybe this flow send from S1 to T1. And then another flow, S2, T2. It's like you send it by amount of 10. So H is kind of the demand, all right, that you want to satisfy. And you should really think of each demand to be like totally different kind of things. Let's say like the first demand here is maybe oil, and this one is water, like different thing. Okay, that's the picture that you should have in mind. And now I can define the concurrent flow. We say that H concurrent flow, script S, script F here. This is a collection of ST flow that you like, such that each of these ST flow have total value, satisfy the demand of that pair. Okay. So to write it like this is just, to write it in mathematical term, it's just a set of ST flow such that each ST flow satisfy the demand. Forget about congestion for now, right? You have a set of demand and you have a set of ST flow for each of that demand. That is a H concurrent flow.
The S1 and S2 are both of them representing the S, or they are two different vertices?
There can be different vertices here. Yeah.
So the commodities are different before.
Yeah. Different commodity. Yeah. Right.
Also, there's no direction, right? So it's like a flow from S to T, also like flow from T to S.
So in our context, we will talk about undirected graph. So yeah, but you can really justify H concurrent flow when the demand is directed to. That makes sense. That is, it just extends to directed graph.
And the flow function will also have 1 and 2 for it.
1 and 2 what?
So because there are two commodities, so flow function will also have subscript 1 and subscript 2.
Yeah. So I really have a subscript ST for every H, for every demand here. Yeah. And each of the flow for this demand should have total value to satisfy the demand that you want for that demand. Okay. Let me like maybe give some example. Let's say that maybe the graph is like the graph G, maybe the graph H is again just two demand. This is 1, this is 2. And then if the graph G, maybe it's like a cycle. Maybe like this to be more interesting. Yeah. This is H. This is G. And let me write it with color. Yeah. Then for example, the flow can look like, the H concurrent flow can look like this, right? Maybe I write it red. Yeah. One is just, you send it this. This is just a flow, flow 1. And another flow is to satisfy the second demand. You just draw it here. And this should have maybe value 2. And note that because this is a flow, you don't need to put everything in one path, right? Suppose that I have more edges. For example, I have more edge like this. I might actually just send flow here 2, and here 1, and they come together here 2. It's just a flow, yeah. And all right. So when we say that this is a multi-commodity flow, you should think F kind of simultaneously routes all the demand. They satisfy all the demand simultaneously. And a way to think of this is we will use this terminology too, that F kind of embed H into G. That is each of the H in H now kind of embed as a flow in G, right? That is something that you should have in mind. H is kind of put into G. Yeah. So that's why this H concurrent flow sometimes people call it the flow embedding. Yeah. All right. We can also call it multi-commodity flow. And once you have defined the flow, we can again talk about congestion of multi-commodity flow. And the congestion here, the congestion of F on every edge here, how to do it? You really just summing the congestion on HE, summing over all commodity, over all demand. For example, if I don't have here this, but the red flow here really use the same edge, then the congestion on this edge accumulate for every demand, right? Okay. And the congestion of the whole flow is just, again, summing, you look at the worst edge with the worst congestion. Yeah. Right, and if the congestion is 1, or at most 1, we say that there is no congestion or it's feasible. If congestion is 10, if you decrease it by a factor of 10, it's become feasible. That is just multi-commodity flow. Any question about the definition?
Can also all terminals share the same?
Yes, right. So H might not look like this, right? H can really look it might look like a cycle itself, or it can look like a clique. But it's just that for every edge in H, you think of it as a demand. Yeah. That is, each edge might not be disjoint. Yeah. Does that answer your question? Or? Okay. More question? All right. So now comes the kind of important definition again. So when I have H and G, I have the demand H and I have G. If that actually exists the feasible H concurrent flow in G. That is, if I can embed H into G, then we just say that H is embeddable into G, or the demand H is routable in G. Make sense? Like very natural way to talk about this. And I will denote this by H is kind of flow-wise less than G. Why? Because think of G have big enough capacity. It's big enough so that you can embed H into G. So G is kind of in some sense it's bigger than H. Right? It's bigger in the sense that you can embed H into G. And actually, you can check that this is really the partial order between graph. But let me, before going to that, let me tell you more about terminology. And we will say that if the demand H is routable, but with some congestion Q, or embeddable into G with congestion Q, if now that concurrent flow have congestion at most Q. Okay. So yeah, again, like when you say that H is embeddable into G, then G is kind of well connected enough or have big capacity enough to support the demand in H. And by the way, from this definition, you can see that when H is embeddable into G with congestion Q, then it means that H is less than QG. That is, if you scale up the, I forgot to say, what do I mean by Q times G? I just mean that this is just the graph where you scale up all the capacity by a factor of Q. Right? So, and I can also talk about like G plus G prime. This is just the graph where you add all the capacity between all edges. But you can see that if H is embeddable into G with congestion Q, if you scale up the congestion, the capacity of G by Q, then it's not embeddable with no congestion. Right. And yeah, you can try to check that this notion of flow-wise less than, like H is less than G in this flow sense is really like a partial order. If you can embed G1 into G2 and G2 can be embedded into G3, then G1 can be embedded into G3. Yeah. And all the like all the algebraic thing that makes sense that should hold just holds. Right. All right. So now I can define the main problem that we will try to look at. It's called maximum concurrent flow. In this problem, you are given a graph G and demand graph H, right? And basically, you would like to find a feasible H concurrent flow. But if you send if your demand is just H, it might not be feasible. So you basically ask, what is the maximum scale tau, such that if you scale this by tau, then the flow is still feasible. You would like to find a feasible tau H concurrent flow with maximum tau. right? So yeah, you have a bunch, you have H and you have G, and you have a bunch of demand. You would like to send it concurrently with some scale, as long and that scale should be like as big as possible times tau. You want to find a maximum tau such that this tau with this scale of tau, there is still a flow. That is still feasible. So, and we just denote this maximum optimal value tau star. I just denote it by like MCF of GH, like maximum concurrent flow of GH. Okay. So just to be clear, like if H is embeddable into G if and only if this tau star is at least 1. Right? So that is the maximum concurrent flow problem. And so let's observe first that this problem really just generalized maximum ST flow problem. So why is that the case? Well, that is just, you just consider when the demand is just one edge. Like when your demand graph contains just one edge, S and T, right? ST. Then you can see that the maximum concurrent flow to satisfy this demand ST, you really just like ask for the maximum flow value to send from S to T, as long as it is still feasible. That is like this value is exactly maximum ST flow. By the way, this is analogous to H expansion, right? When H have only one edge, S and T, the phi of GH here, you recall, right? That is just minimum ST cut. So in other words, we actually have that for any graph, then like to write Max-Flow mean cut theorem in this notation, you have that the concurrent flow of G for this single demand is just is a H expansion of G when the H is just single H. So this is like kind of, it means that this thing, like maximum concurrent flow for maximum H concurrent flow and H expansion are really like tightly connected, at least for a single demand case. But is this true for every demand? We can ask. But no, it is not. But we will see that actually it's still kind of true approximately. So actually, we will see that this is now the generalization of Max-Flow mean cut theorem for any demand, not just single demand. We will see that at least for undirected graph, and this is important. In undirected graph, it can be weighted, that's fine. but for undirected graph, you have that the max flow is max H flow, max H concurrent flow is kind of similar to mean H cut within log n factor. So this is called approximate max flow mean cut theorem for concurrent flow. And there are other variants of this theorem, which is interesting too, but this time we will talk about concurrent flow. Yeah. And by the way, this actually doesn't hold for directed graph. Any question about at least the statement of the theorem? This is a goal today. We will try to prove this.
Sorry, probably a stupid question.
Yeah, please.
Is there a simple reason like why the MCF exists as a maximum value? Not probably a super value.
Why MCF exists at all? Well, MCF, like you can put 0, right? MCF can be 0. So I mean, there exists some value for sure, because if you don't send any, if you just put this to be 0, then any empty graph can be embedded into any graph, right?
Right.
Yeah.
But what if like it can be approximate to a certain value, but not exact that value? Is it possible to have such a simple?
Can you say again? Sorry.
Like for example, like you can define a sequence of increasing numbers such that it has a limit value like 1 or some value, but for all real value that's less than 1, there's always exists some immutable h that can achieve, but for exactly the next like supreme value, it's not immutable.
Oh, you asked about like supremum and maximum. Why like okay? So you will see why actually, but the reason, the quick answer is that you can model this problem as an LP. Yeah. And you can solve LP, and you get the maximum one. More question?
Can you all solve LPs? I thought it was like you could only do it if the weights were like rational or something.
Oh,
So maybe it's right. Maybe it's possible.
well, an LP is just like a like intersection. LP is just intersection of half space, right? So you have a polytope, and if you want to, like LP always have a maximum optimal value.
Simplex that might not work. I guess the simplex that works.
So that is, I guess I think.
I thought it required like the edges or like the coefficients to be all rational or something, because like you couldn't show that simplex always where.
Well,
Actually, no, I don't remember it, but I remember I saw this.
I also think that quotient should be rational. If not, the same kind of things can't be.
one sec. So if you have an LP, if you ask mathematical question, right? It exists.
I agree.
It depends on the algorithm. Yeah. So okay. More question about this theorem before we prove.
So I just have one doubt in the little previous part where we have multiple paths and we can direct the flow in those paths. But then at any vertex, because there's no direction, so I'm kind of little vague there. How will the path of feasible flow is defined because there's no direction at a vertex?
Well, so So you like if you have a graph G and then there is an edge E, you really just the path, like the flow path have no direction. You really just look at all the paths that contains E. All of these paths, each of them have some flow value, right? And you just sum this value up. Like it doesn't matter, there's no direction really. But you just sum the value over all path here. And if this value is less than the capacity, that means the congestion of this edge is at most 1. Just sum the value over all path.
So we won't sum it over for a vertex, we will sum it over paths. So there's an inherent direction that's there.
There's no direction. And you don't sum over all vertex. Like there can be this vertex here. That is the neighbor of this guy, but still there can be many paths that go through this vertex, right? There can be like other path here, this path here, this path here. You don't look at all the neighbor of an edge. You look at all the path that contains this edge. Okay, let me proceed. So let's prove one direction. And this is gonna be a direct argument. So what do we want to show here actually? This part kind of says that if there is a sparse cut with respect to demand edge, there is a cut in G that is kind of small compared to H. That's what I mean by sparse cut with respect to H. If this thing is small, there exists a sparse cut with respect to H, then the H concurrent flow must be small too. That's what we want to prove. Okay. And why is that the case? So let's say that tau star is the optimal value of the concurrent flow. And let's say that this is F is is the maximum flow. Okay.
Sorry,
Yeah.
I'm actually a little confused though. Like I thought this phi of GH, it had something to do with like weights. Like it was like sort of, you were looking for the minimum cut metric or something.
Oh, good. So let me recall this. I used to write it like this thing, right? G S. Sorry. And now we think of weight and capacity as the same thing. So we really just, all right. So when this thing is small, it means that there is some cut S such that the cut size in G, the total capacity of this cut in G is small compared to the like a demand crossing to the capacity of this cut in H.
So having small conductance is bad for us.
I don't hear you well, sorry.
So having small conductance means it is bad that we cannot satisfy the demand.
Yeah, right. So that is, if this is small, it means that the demand crossing the cut is big compared to the capacity in the graph. Make sense? Yes. All right. And that kind of really is a kind of, if you have this picture in mind, it kind of gives the proof already, because suppose that just look at any cut S here, right? Maybe there. Look at this cut S, and we know that. So this is the cut S in G, and look at the same cut in H. Okay, and any H, any STH crossing this cut is a demand that which says that if this is a like, let's say that this you have some like H concurrent flow in G, this demand means that you must have some flow satisfying this demand, and the total amount of flow that cross this, it might cross in the bad way, actually it might cross many times, but at least the total capacity that cross this cut must be at least the demand of this H, must be at least this. So for each demand, it consumes the capacity by at least this much. Consume the capacity of the cut in G by at least this much. So it means that the total unit of flow that cross this cut in G must be at least, so note that F actually just satisfy each demand after scaling by tau star. Right. So the total unit of flow crossing the cut is tau star with this. You just scale it by tau star. And now if you sum over all like a demand here, it means that the total, like, this is just the total demand that cross the cut. It means that the capacity must be at least that, because the flow is feasible. And for each demand, like there are this total many demand that must cross this cut S here. But it's feasible, so the capacity must be at least that. Okay. Right. So now after like arranging, you have that tau star can be at most this ratio, which is exactly the H expansion of a graph. So there is really nothing much here, really. Like you just say that, okay, if there is a sparse cut with respect to H, like there is a sparse cut where like there is a lot of demand crossing the cut compared to the capacity, then you just like the maximum flow cannot be big. The flow that really satisfy all this demand cannot be big. All right. And now, so that is just one direction of the theorem. Now we will prove another direction. But actually, the way we will prove is just to prove the whole thing in one go. But now we will use like an indirect argument, and it's not like maybe not as intuitive as this one. So what we will show is actually this. We will show that the optimal concurrent flow will turns out to be exactly the same thing as the thing that we have learned last time, the latent round relaxation. So they actually are the same. But last time we have seen that latent round relaxation of phi is just a good approximation with log n factor. So, and because of this key lemma, you immediately get the Maxwell-Minkut theorem. Okay. So let me try to prove a key lemma here. And just for notation convenience, let me actually rewrite things a bit. Instead of writing here as a capacity of H U to V in G, I write it like C for capacity, CUV for capacity. If there is no H, there is no H, then the capacity is 0. Right? And because we think of each H in the graph H as demand, we write DUV for demand. Again, if there is no H, then the demand is 0. And okay, so that is just two things, that's just notation. And now, let's see. Let's try to see that we can actually model this maximum flow problem, maximum concurrent flow problem as an LP. You can just write it as an LP because why? Look. What we want is just we have a bunch of paths, right? Like basically all possible set of paths. Like a path from U to V for any UV, and the flow really just assign the flow value on every path. Okay, and what we want to say is that first of all, it should at least satisfy the demand. Actually, it should be equal, but if it is not equal, like you can just write it like at least 2, because the optimal value in the optimal value version you will have equality anyway. So what does it say? It says that the total flow value from U to V is at least tau times the demand, right? And at the same time, you respect the capacity. All the path that contains an H, UV, is at most like summing over all the value. This is at most the capacity, and you just want to maximize tau. So this is, you can see, right? This is exactly a concurrent flow problem. But once you have an LP and you want to analyze things, it's just always good. Sorry. When you have an LP and you want to analyze or understand it algorithmically or structurally, it's always good to write a dual and interpret it. Right? You get like just another way to think about the same problem for free. So we can write a dual, and it looks like this. And you should try to verify that this is the dual by yourself. Or if you want, I can show it in the exercise session. But I really encourage you to try, because the skill of deriving dual LP is really important, I think, to do research in TCS. Like very, very good thing to have. Okay. So let's try to interpret it a bit, right? What is this thing? like there are like a two set of variables x and y, and what you want to do is that you need to like kind of distribute y like this. You need to like distribute y so that at least the total, like the weighted sum of y is at least 1. Think of y as a kind of distance between u and v. You want to assign like a point u and v so that y of uv is in total is kind of bigger than 1. Why do I say that this is a distance? Because if you look at here, like if y uv is here, then this constraint says that if you look at any path connecting uv, any uv path, then the total length in x must be at least y. Right? If you're summing up overall x along this path, must be at least y. Okay. And but at the end you would like to minimize x, total x. So it's like you kind of assign weight. You assign x weight in the graph, and you want to like the total weight in this graph. Like think of this as capacity of h uv, and x uv is like a length of that h. So here what it means like you want to minimize the volume of a graph, right? Like you have this is capacity uv, and let's think of capacity as a width. This is capacity, and this is xuv. xuv you think of it as a length. So this is like this is the volume, the total volume of a graph. All right, and what is this? It says that the length between uv in x must be at least y uv. So y uv is literally like a distance between x and y. And here it says that in average, like the total distance like should be kind of at least 1, but you need to certify this somehow so that at the end the total volume is small. Does it make sense or? All right. So this is just some interpretation of the LP. Okay. All right. So but anyway, we have that the maximum flow, maximum H flow is the optimal value of the primal LP. But by strong duality, you also know that this is the same thing as optimal dual value. So now how can I prove that so it's enough if I can show that the optimal value here of the dual is the same as the latent round relaxation, and that's the goal that we want to prove. But let's try to recall latent round relaxation a bit. All right. So let's look at what we have seen before. Here, this is latent round relaxation. You have that you minimize overall metric space, metric D, such that the total weight in H is 1 and you want to minimize the total weight in G. Right. But I just rewrote this as here, right? Recall this. The weight in G is capacity and the weight in H is the demand. So come back to this. We have this thing. And note that like I used to write this as equality, but again, even if this is not equality, if I just write it at least, we know that the optimal value must be, this must hold with equality anyway, because you can always scale it down so that this holds with equality, right? So we have two LP. This is the first, this is this one, and another one here. So let me actually put it side by side. Oh, yeah. We have two LP that look similar, but we want to show that they are like the optimal value are the same. So how to do this? Well, what we need to do is just that, like, kind of given the solution in D, we can find a solution XY such that the objective is at most that, and vice versa. Once we can do that, we are done. Right? Given XY, you can find D too. All right. So we will do exactly that. And so how to do that? So suppose that I have solution. What I will prove is this direction. All right. So this is DLP. This one is LR. GH. Given a solution XY from the LP, I can define a D, so that the objective is at most the objective from XY. So, and that would prove this thing. So given XY, let me define D to be just distance from U to V with respect to X. So think of X as a weighted graph, right? So it's a graph defined by X such that each edge here have weight XY, X have weights defined by X. So I can define the distance in this graph. And note that if I just define it like this, then let's observe this. That the distance, this distance is gonna be at most X UV, and that is kind of trivial, right? Because there might be like a path which is shorter than this edge itself. So that is why this is true. But you also know that y is the lower bound for the distance. Why is that? Can someone tell me? Yeah, it's from this constraint exactly, right? So for any path, if you sum up the distance in X, it's always at least Y. So you have this too. And you can just now verify that with this definition of D, we have we have that. So first of all, the objective here is at most the objective from this LP. So the objective is better. And is it still feasible as well? Why? Because this is at D is at least Y, but Y this thing is at least 1 by this constraint. So this constraint is still true, still holds. And other inequality, other constraint will be trivially satisfied because D is a metric. So yeah, we have one direction. This is done. And now to prove other direction, just for convenience, let me write something like this. That is, I write D of P. It's just a sum over all D along the path. All right, that's just for convenience. For example, the constraint here. The constraint here is just the same thing as writing that xp is at least yuv, right? Okay. And now there is just some easy exercise first, which says that if you have a function that satisfies triangle inequality, like a metric, right? Then for any pair of nodes uv and any path from u to v, you would have that the distance like d of uv is at most the total length of the path. So let's. You can try to prove this. So that is, if you satisfy triangle inequality, then it will be the case that if you look at any path like this, you used to have that this thing is at most this, but now this thing will be at most the total length here too. All right. Just some fact that we will use. And now, okay, let's prove this. So we want to say that given the solution in latent round relaxation, we can find a better solution, or at least as good. So given the solution D from latent round relaxation, I will really just define X and Y to be the same thing as D. And so now it's just like we just need to check that that all of the constraint is still whole. So shoot. Hey. Good. Wow. Okay. So, okay. So you used to each constraint will still hold, right? So D used to, you used to have this, but now you define Y to be D, so this still hold. And here you just replace D by X, so they're the same. And what about this thing? You used to have that D satisfy triangle inequality, but now this thing is just the same thing as us saying that this is at least that. So we are done too. So yeah, we now have that they are the same. The max flow, max concurrent flow of GH is the same as LR relaxation, latent round relaxation, and that complete the proof why of McFlow min cut theorem. Okay. Question? Okay. So, by the way, I want to point out that this factor log n, you may wonder if it can be improved. Like why it's not exact, can it be O of 1? But it turns out that it is the best possible. And this is what people call flow cut gap. So there is no flow cut gap for single commodity flow. Min cut and max flow are the same. But for multi-commodity, there is a gap of log n. And I will try to write some step in the homework, and you will prove this. And just a spoiler, the graph that you will see that there is a gap. By the way, what do I mean by a gap, right? I mean that like you have, like, let's say this thing is big, but the flow is small. So actually the G, think of it as a complete graph. And it turns out that when H is a constant degree expander, then you have this gap. But anyway, this will be in the homework. Yeah. All right, and okay, just to conclude, we have that max concurrent flow generalized ST max flow, and we can indeed compute max concurrent flow in polynomial time. Well, this, like the LP that we have seen, actually is not like the best LP. Why is that? Because it has like exponentially many variables. Seems bad, but there are several reasons why you can actually compute it in polynomial time. Can some of you tell me? Yeah, that is one reason. If you just want a value, then you can compute it by looking at the Redenlau LP. Yes. You can also really get the flow, though. One reason is, first reason is that you can use ellipsoid actually to compute this. Because do you know ellipsoid actually? Can you raise your hand if you know ellipsoid? Okay, so ellipsoid is just some algorithm such that for like certain type of LP, you can, even LP has exponential size, you can still compute it. But actually there is another reason, because you can actually rewrite this LP so that it's equivalent, but it has polynomial size. Why is that? Just think of maybe max flow problem, right? Just single community max flow problem. you can also write MacFlow as this kind of LP as well, right? That is, you want to pack a lot of ST paths, and there are like exponentially many paths, and that is bad LP. But you know that there is another LP that capture MacFlow too. What is that LP? Well, you just say that, okay, it's an LP where like you write a constraint to be something like for every node, U flow in of U equals flow out of U, except at S and T, and you want to maximize flow into T, something like that. So, and there are maybe some other constraint, but you can see that this LP will have polynomial size, and you can extend this kind of LP to multi-commodity flow problem too. Just by really just add a bunch, just add some more constraint. Yeah, maybe I talk about this in the exercise session. Yeah. But yeah, you can compute it in polynomial time. And H concurrent flow has close relationship to H expansion via MacFlow min-cut theorem. So let's interpret this just a bit, right? It means, what does it say here? It says that if there is a sparse cut with respect to H, then H concurrent flow must be small. This is this direction. But it says here also that for this direction that if actually there is no sparse cut with respect to H, then you can indeed fly some flow, which is quite large. But maybe you lost this factor, log n, but still quite large. All right. Okay. So, by the way, I would like to talk a bit about maybe I talk about something else. Sorry. I will talk about projects maybe for this last 5 minutes. So how this will work? You can try to form a group of people, maybe 1 to 3, that you will work together. And I will put this in the canvas soon. And basically, you can skim through the list of projects that I will list below and choose which you want to do. You can also suggest something to me. But I suspect that each of these projects might take you some time, like a month. So it would be nice to look at it and start early. And the main task is basically try to understand the goal first. Talk with me maybe and really understand what is the goal of the project. And then try to think about the solution as soon as possible. You can try to just directly attack the problem or read the related paper, which I will list it below as well. Yeah, and discuss with people in the group. And if you get struggle, or like we can just meet and talk. So it's like a research project. And the end result is gonna be like some report. It should be like not like the page limit, like the page here, like it should be at least 6 pages, just to make sure that you spend some time and think about something, have thought about something, but it can be longer, it can be real paper. That would be perfect, right? So what we need to do in the report, you need to explain the problem, what is known, and what is known about the problem, and what is like the goal and then you need to write down the solution, like of the open problem that you look at, but it might not be a solution. It can be partial solution, or you might not solve it at all. Just write down the attempt that you have tried. That's good enough too. It's just the goal is really just you have some experience in looking at the problem in this area, and have fun thinking about it. No pressure. And the problem that, so let me talk about some problem that is kind of, I think it's really possible for people to try. So the first thing is a small open problem. Is all of this is, I kind of see high level approach how to like attack it, and we can just talk and you can try to read papers and try to make it work out. So you will really learn some nice technique by just trying to solve them. It might not be publishable, but actually it might be. I'm not sure, but it's not gonna be groundbreaking, because at least some expert like me already know how to approach it. So it's not that surprising, but still kind of nice. So the first thing is the problem of something called feedback vertex set. So what is this problem? This problem is just the following. You have a graph. You ask how many nodes you need to delete from the graph so that there is no cycle in the graph. Clear? Like you have a directed graph. You want to delete few number of nodes as possible, fewest number possible of nodes, so that the graph become a DAG. You want to delete all the cycle. And people have shown like a log-n approximation algorithm for this, but no one has shown how to do it fast in linear time. And later in class, we will see something about expanded decomposition. And I think that if you generalize the notion to directed graph, and we can talk about what should it be, and you should be able to solve this maybe with polylog approximation in linear time. So that is like a kind of nice and if you can solve it in log-n approximation and still fast, I think that's a good result. Yeah. So is this problem clear, by the way? Okay. And next problem is about dense set subgraph. You have a graph, and you want to find a subset such that it contains, you compare the number of edges inside a subset with the number of nodes. And that is density of a subset. And you want to find a set that have maximum density.